So we left off, we were talking about things like one-to-one functions. We can now even introduce how we can find the inverse of one-to-one function. And it's going to involve a fairly straightforward process. Remember, a one-to-one function is one that not only passes the vertical line test, making it a function, it also passes a horizontal line test, meaning that you can't have different x values mapping to the same y value. So that's what that will mean. So to find the inverse of a one-to-one function, first of all, use y instead of f of x, at least for the purposes of just doing the inverse calculation of finding a function's inverse. Once you do that, you're going to need to interchange x and y. And I don't mean, that's not a fancy word for anything. I mean literally everywhere you see a y, slap an x in there instead. And everywhere you see an x to start with, slap a y in there instead. Just completely interchange them. Step 2, you're going to solve for y. And then step 3, you're going to go back and just say that you're going to go back and say, okay, now that I've done all that, I have found the inverse. You're going to use this kind of symbology for it, f. It looks like that's a -1 power, which is not exactly the case, but it is the symbology we use to say f inverse. So it's going to run fairly smoothly. Technically, you should verify that the function you're starting with is one-to-one in the first place, that it would pass like a horizontal line test. But usually that's going to be something that you ask for forgiveness instead of permission. You're just going to kind of barrel through it and assume that it is one-to-one to start with, and then proceed from there. So let's see, let's start. Let's find the inverse of, let's start with an easy one. Let's say our original function is just 3x minus 5. So starting with a simple linear function with a slope of 3, y-intercept is 0, -5. And it's a pretty simple function, so finding the inverse is going to be pretty simple. The first thing you want to do is, instead of calling it f of x, call it y, at least for our purposes here. At least for our purposes. So that was kind of like the pre-step. Then now the real step 1, we're going to want to interchange x and y. And so we're going to pull a Freaky Friday, or I think there's a new Freaky movie coming out with Vince Vaughn soon. We're going to do something like that, and we're going to body swap these. And it's exactly what it sounds like. Where once there was y, now there is x. Where once there was x, now there is y. The first shall be last, and all that business. So we flip-flopped them. So we've done step 1, very good. That was kind of the easy step. Step 2, we need to solve for y now that we have it like this. We need to get y by itself. All right, so let's think about what's plaguing y. Well, this -5 here, so let's add it to both sides. you're going to end up with x plus 5 equals 3y. Next up, this 3 here is plaguing y. So you're just going to divide both sides by 3. So you're going to have y by itself, which is what you're wanting. Now over here, I'm going to split up the numerator. You can leave it like this technically. It's not wrong, but it's not very helpful. So I'm going to split up the numerator. I'm going to say that's x over 3 plus 5 over 3. Which of course you could do, because if you were to add them back up together, they already have the same denominator. You would just get back to this thing here. But we're going the reverse direction. We're going from here to here because this is just kind of a better way to write it. And so finally, with the y, we usually like it on the left-hand side. So all I'm going to do is flip them, mirror reflection. I'm also, instead of doing x over 3, I'm going to say that's 1/3 times x. Plus, and then you can just say 5/3. Nothing too wild going on there. So done. The last thing we're going to do is we're going to call y f inverse of x. So goodbye, good y. You are actually called f inverse of x. Oh my goodness. It's at the bottom of the screen, so it gets all funky. Wow. I can do it. I believe in myself. There we go. F inverse x. And there you go. We have found the inverse function of the function 3x minus 5. And as a brief refresher, the inverse kind of undoes the effects of its original function. So in this case, 3x minus 5, and then 1/3 x plus 5/3, those two, whatever value you plugged into one of them, if you then plug the output of that into the other, you'll get back to the original starting value you had. It's like two machines where you put a lump of clay into the first machine, it warps it, changes it, but then when you put it into the second machine, it brings you back to the original lump of clay untouched. So that's kind of the whole point of inverses, is that they undo the effects of one another. And that's precisely what is happening here. How about we do another example? Find the inverse of. Let's pick a fun color. Let's do purple. I wish they had a darker purple, just because purple's a very royal, powerful color. So let's say you've got the square root of -3 plus x. And we want to find the inverse of this function. We want to find the thing that kind of undoes this function. So remember, our first step is going to be to call this y instead of f of x. Simply because it makes the process run smoother. I don't want to have to interchange f of x and x. It just kind of looks sloppy, or it's not very succinct. So just call it y instead. You'll undo it in the end. Now we're gonna perform some magic here. We're gonna interchange x and y. So we're literally just where you see a y, now you see an x. I'll make it that big. You still have this, then it's negative 3 plus, now it's y, negative 3 plus y. So we're going to end up with something like this. Now we need to actually solve for y. Now that we can't just uninterchange them, that's not how it works. We need to solve for y, assuming that now that they're interchanged, they're stuck in that form. So we see that the first thing is that the overarching right-hand side is plagued by this giant square root. So using some of our wisdom we've picked up throughout the months here, we're going to square both sides. Square. Let me give myself a little more space over here. And we're going to square this side. Leaving us with x squared on the left-hand side equals negative 3 plus y. The square and the square root cancel each other out. They're opposite operations, which makes perfect sense because we're taking the inverse. We're trying to find kind of the opposite function. And so it's kind of apt that we're going to be doing that. Okay, so we're now here is our new reality. Now, again, we're still trying to solve for y. The only thing bothering y at this point is this minus 3. So we'll just add 3 to both sides. So we're going to end up with x squared plus 3 equals y. And we've done it. Now, normally we like it to be y equals, we like y being on the left-hand side. Well, that's perfect. It's equality. It's symmetric, meaning I can flip it. It's just y equals x squared plus 3. Very lovely, very beautiful. And then remember, we're just going to go back and call this the f inverse function. Now that we've done it. The y was convenient notation while we were solving it, while we were working the system. But now we're going to go back and use f of x and f inverse of x and all that lovely business. Okay, so pretty straightforward. We found the inverse. Very nice. And we'll leave this section off with important facts about the inverse. A few important facts, something we don't need to spend too horribly much time on, but important nonetheless. If your original function f of x is 1 to 1, its inverse exists. We kind of already established that, but basically being 1 to 1 is entirely necessary for inverses to work. And it's because what the inverse does is normally a function maps x values to y values. Normally a function says, okay, input this x value, I'm going to spit out a y value. But what the inverse does is it goes literally backwards, the opposite direction. The inverse says, okay, starting with this function, what if I spit in a y value, what x value is that going to barf out? That is what we're looking for with the inverse. So the inverse is literally exactly what it sounds like. It's inverted reasoning. It's going the opposite direction. So if it's something's 1 to 1, that means that you can't have a single or multiple x values going to the same y value. so that when you try to spit in a y value, it doesn't try to spit out multiple x values. That's kind of the whole point behind it. Imagine, let's draw a nice little picture of this situation. A nice little graph. Imagine not dragons, but this function here. It can be curved. It can look something like a polynomial, maybe a third degree polynomial. Now, first and foremost, this thing passes the vertical line test. If I run a vertical line across it, it's never going to hit the function multiple times. Remember, the arrows aren't actually on the graph. They're just indicators on the graph. So it never hits the function multiple times. However, this thing clearly fails a horizontal line test. If we run a horizontal line up and down the graph, it's okay, it's okay, it's okay, it's okay. Ah, there's a problem. The horizontal line hits the graph multiple times. So this thing passes vertical line test, it's still a function. It does not pass horizontal line test, so it's not an invertible function. It is not one-to-one. And now if we think about it, that would mean that if I'm going the opposite direction with the inverse, whatever this blue thing is, its inverse would take in y values and try to spit out a single x value in order to be a function. But look, if I take this y value, let's say this was y equals 1 here, it would spit out this x value, and this x value. So being one-to-one is necessary for being invertible so that the inverse itself is a function. Because the inverse wants to be a function, it wants to only spit out a single value for any value you plug into it. So that's why being one-to-one is necessary. That's why it's important here. Imagine we had something that looks a little bit better, something that was monotone, meaning it's always going one, either strictly increasing or something like that, and perhaps not that. Imagine a function that was just decreasing the entire time. No matter what, it was always decreasing. It could look like it flattens out in parts, and this is not very pretty, I'll admit, so bear with me. But imagine something that as I went from left to right, it was just constantly decreasing. Now it passes the vertical line test. You can clearly see that. Doesn't take too much time to verify that. Oh, yeah, it's never touching the function more than once. It also is going to pass the horizontal line test. If I run this horizontal line down, it never touches the function multiple times. So that means whatever this function is, even though it's ugly to look at, it is a one-to-one function, so it has an inverse. That means that any y value I pick, you can plug a y value into the inverse and get just a single x value popped out of it. And that's what we want. That means the inverse is a function. So that's kind of the value behind all this. Oops. So we need a function to be one-to-one in order to have an inverse. The domain of f of x is the range of f inverse and the range of f of x is the domain of f inverse. So that's exactly what it sounds like. Basically, a function and its inverse are flip-flopping their domain and ranges. The graph of f inverse is a reflection of the original function about the line y equals x. So let me demonstrate that. So whenever you have a function that can be inverted, meaning you're starting with a one-to-one function. So here we go. Let's say you're starting with the square root function. We started a little bit better here. The square root function, remember, it kind of just steadily rises. It's concave down. It's kind of not getting to its point anytime soon. This is the inverse function here. Here is the line y equals x. It's not going to be an actual function that we're looking at. It's going to be a line by which we can reflect this one here. So here's the line y equals x. The inverse of the square root of x function here is going to just be a reflection about this line. So imagine I was a better drawer. It's going to be a total reflection about it. So let me actually draw that here. I mean, it's okay for them to cross through the line y equals x. So it just reflects about that. You can create some kind of interesting art shapes out of that. And that's really all the inverse is going to do. It's going to reflect about the line y equals x. Which is a little bit weird. We haven't really talked about reflections about y equals x. We've talked about reflections about the x-axis or the y-axis. But it turns out you can reflect about any line you want. In fact, theoretically, you can reflect about any function you want, even if it's not a line. Although drawing that visually, it causes some warping and stuff, and so we don't go into uber detail about that. That's kind of an interesting idea. Finally, if a comma b is a point on f of x, on the original function, then you can flip-flop them. B comma a is a point on f inverse. So the inverse just flip-flops the x and y values for any point on the original function. So the next question you're probably asking is, why do we even care about something like this? Why do we care about inverses? Why do we care about what their graphs look like, their reflections about the line y equals x? Well, now is the time to get into the real meat and potatoes of this chapter. We start with a little talk, preamble about inverse functions, but now we need to jump in to the whole point of chapter 4, which is to investigate exponential and logarithmic functions. Exponential and logarithmic functions. You might be comfortable with exponentials to a degree. You may have seen logarithms before. But what we're going to find out is that the exponential function and the logarithmic function are inverses of each other. In other words, they're opposite operations. But let's not get too far ahead of ourselves. Let's introduce everything in time. This is going to be section 4.2. That's the section symbol. I'll try to draw it a little better. Imagine it was like a snake or something. That's poor. That's a very bad job. I drew it better up here, so why even fix that? We're going to get into section 4.2. exponential functions. So we're going to define a few, we're going to define the exponential function itself. We're going to define a few very simple vocabulary words that are attached with the exponential function. So let's do it. The exponential function, we're going to say that's a new definition. The exponential function with base b is given by, so it's going to have something called a base, which is, you probably can guess what that is. It's going to be a function, so we can write f of x. It's going to be that base just raised to the x power. So it involves an exponent, as you probably would have guessed, because we're dealing with the exponential function. So there you go. You have a base b. Now, it's a little bit weird because x is the variable and you're saying b is not a variable. Well, it's because when you're actually doing when you're finding exponential functions, you're going to have a realized base. You're going to have an actual number here, and x will still be x, the variable, and we can analyze that. So this is just to kind of write out the general model. We have a few restrictions, though, on b. B has to be positive. You can't have a negative base and be an exponential function. You can still take negative numbers and raise them to exponents, but you can't make a function out of that process. Not always, or pretty much you can't at all. And that's because, well, I don't want to ruin the surprise. So the base has to be greater than 0. Also, we don't want a base of 1. We want b, our base, to not be exactly 1. Because if it's exactly 1, it's boring. Raising 1 to any power just produces 1. 1 to the 4th power is still 1. 1 to the 100 millionth power is still 1. 1 to the negative 5th power is still 1. So it's not interesting raising 1 to different powers of x. We don't care about that. But b can be a number between 0 and 1. It can be 0.5. It can be 0.3. It can be 1 over 7. It can be 3 over 19. B can be any number between 0 and 1, and it can be any number greater than 1 as well. So let's play around with this. Let's play around with this. Let's talk about this function. Let's use orange. Now Halloween is past. That makes me very sad. I always say wake me up when September ends because I love the month of October. But Halloween is gone. We'll see it next year though. And we've got Thanksgiving to look forward to, and we've got Christmas to look forward to. Well, hot dog, I'm excited about those things. But Halloween is very special because it's fun. So let's say your function is 3 to the x power. Let's find f of 2. And we're going to do this for a couple different functions. Okay, f of 2. So just because we're dealing with this new thing, f of 2 just says plug a 2 in for x. Is it any crazier than that? No, not a bit. So f of 2 is going to be equal to 3 as the base. We can't change that. We're just plugging a 2 in for x. So it's going to be 3 squared, which is 9. And that's all I've got to say about that. That's it. So 2 is the x value, 9 is the y value. So 2, 9 is a point on the graph of 3 to the x. That's what that means. Now, let me plug in my laptop. It says, Josh, I am hungry. And I say, well, then you ought to be fed. Let's do this for a couple others, and we're going to mix it up a little bit, have some fun with it. Let's do pink. We never do pink. Okay, let's say you're starting with the function f of x equals, now our base is going to be the fraction 1/4. And so it's 1/4 to the x. Okay, and what we want to find f of 3. Okay, so again, it's really not any harder than you imagine. F of 3 means plug a 3 in for x. So you'll get 1/4 cubed. There's a couple ways you can do that. If you know certain exponent laws for fractions like this, you could just say it's 1 cubed over 4 cubed. Another way you can evaluate that is to just tell yourself it's this. 1/4 times 1/4 times 1/4, which is true. Cubing something, you're just multiplying it to itself 3 total times. 1 times 1 times 1 on top is 1. 4 times 4 is 16. 16 times 4 again is 64. And that's it. So the point 3, 64 is a point on the graph of this new f of x. Let's do a couple more, but let's ramp up the difficulty a little bit. Let's try red. Let's say our function f of x is going to be 2 to the x. 2 to the x and let's find f of 5 over 2, 5 halves. Okay, so we have a fractional power here. We're going to have a fractional power here. Now, the way a fractional exponent is going to work, the top number is what you're raising it to. The bottom number, though, is a root you're taking. So this can be rewritten as the square root of 2 to the 5th power. And then remember, when you're taking a square root, you don't need to write the 2 on that perch there. But I just wanted you to see this 2 would have been the perch here. If this was 5/3 power, you'd be taking the cubed root. If this is the 5/4 power, you'd be taking the 4th root here. But when you're taking a second root, you don't need to write the 2 there. And so now this isn't going to be a pretty number, but we can say it's the square root of 2 to the 5th is 2 times 2 times 2 times 2 times 2. So 2 times 2 is 4, times 2 again is 8, times 2 again is 16, times 2 one more time is 32. So we get the square root of 32. So it's important to remember how fractional powers work. We reviewed that earlier in the semester. One more, un más. Let's say our function is just 5 to the x, but we're going to have to put a negative exponent in there. F of negative 3. So, well, let's try it out. That means we put a negative 3 into the exponent. Now remember how negative exponents operate. What it actually means is that it turns into division. It turns into division. When you have a negative exponent, you're actually saying take 1, which there's an understood 1 here. You could always say, take 1 and divide it by 5 to the 3rd power. A negative exponent is actually telling you how many times to divide by. So this can be rewritten as 1 over 5 to the positive 3rd power. And so we're going to be utilizing that all day. We're going to be utilizing that fact all day. 5 to the 3rd, so 5 times 5 is 25. Then we got to do 25 times 5. We got to do it one more time. And so if you come out here and you do the old school multiplication, you'll find an answer of 125. So it becomes 1 over 125, which is ultimately a pretty small number. So it turns out that the domain of the basic exponential function, as long as you don't throw any curveballs in there, you can actually plug negative x values in. You can plug 0 into that. You can plug any positive x value you want into it. So it turns out the domain of the exponential function is going to be all real numbers, negative infinity to positive infinity. This also means that negative 3 comma 1 over 125 is a point on the graph of 5 to the x here. So you can deal with negative exponents. We have a system for doing that. So let's talk about the way some of these graphs are going to look. Let's talk about it. So we're talking about graphs today. We're talking about graphs here. We're going to talk about characteristics of the exponential function. So remember, we're starting off with just some valid base b raised to the x power. Here's some interesting characteristics. So first of all, these are 3 points on the graph. -1, comma, 1 over b. Why? Well, whatever b is, if I put a -1 in for x, that's going to make it 1 over b to the first, or just 1 over b. So this is a point on the graph. The next point that we can talk about is 0, comma 1. If I put a 0 in for x, remember, raising any non-zero number to the 0th power always produces 1. So for instance, 4 to the 0 is 1. 17,000,005, you raise that to the 0th power, you're going to get 1. So raising something, except for 0 itself, raising something to the 0th power gives you 1. Thus, if I put a 0 in for x here, I'm raising something to the 0th power, I get 1 out of it. Finally, if I put a 1 in for x right here, that's just b to the first, so it spits out just b itself. So this is kind of no-brainer here a little bit. We can think about it for a moment and say, oh, okay, these are 3 points that are always going to be on the graph, no matter what b value you choose. 0, comma 1 is especially interesting. That's especially interesting. Number 2, remember, our base just has to be positive and it can't be equal to 1. So there's actually going to be 2 possibilities. If the base b is greater than 1, if it's 1.5, 2, 3, 4, 17, 70 million. If b is greater than 1, your function is increasing always. Meaning as I go from left to right, the function is always rising. It's always going up. It's on the up and up. Now, if your b value is between 0 and 1, so 1/2, 0.3, 0.1, it can't be 0 itself, it can't be 1, but if it's something in between 0 and 1, you're actually talking about a decreasing function. The x-axis is a horizontal, or is the only horizontal asymptote for any exponential function that's basic like this. So this is only true for the base exponential, or the simple exponential. Even I could call it the parent function. That's probably the best word for it. If I try to do some of my transformations, if I tried to put a negative sign in front of x, if I try to put a 3 in front of the base that's not getting raised to the x power, if I do x plus 2, if I add 7 to the entire function, remember those are transformations. And while you can do them, you're no longer talking about the parent function. So you could totally be changing the horizontal asymptote. So just for the parent function. Finally, the domain is -infinity to +infinity. And that's my best attempt at writing infinity. Which means in turn that I can plug in any x value I want that's real. Any real x value I want, I can plug into the function and I can produce a number out of that. The range, though, is a little more nuanced. Let's use that maybe for my infinities. I think that looks a little better. The range, though, is just 0 to infinity. In other words, for the parent exponential function, you're not going to be able to spit out a negative y value because the base is positive. Raising x to negative exponents doesn't make the actual number turn out negative. It just makes it fractional, but it keeps it positive. It keeps it positive. So with these in mind, let's look together, let's investigate some graphs of exponential functions. And I'm actually going to pull up a graphing calculator. So bear with me, an online graphing calculator. Because why draw it by hand when we have really good technology at our fingertips? We've got technology. It's a new age. Okay, it says vote at the top. Is there an election coming up or something? I have no idea. Um, so this is the basic exponential of 3 to the x. So our base is b, simple, 3 to the x. So comparing some notes here, first of all, we see that the base is greater than 1. 3 is greater than 1. Thus, notice we have an increasing function. As I go from left to right, it is indeed increasing. It's going to increase on to positive infinity. It's never going to go below the x-axis. In fact, if I zoom way in, it's going to keep getting closer and closer without ever actually touching the x-axis, which is exactly what it means to be a horizontal asymptote in this case. So already we can see some of those characteristics that I discussed in there. The domain, like I promised, is all real numbers, meaning I can go all the way down to negative infinity on the x-axis, and there's always something. I can go to positive infinity on the x-axis. The problem is this thing blows up really quickly, so it's hard to see. It's going to be very hard to see because graphs are ultimately quite limited. We can only show you so many things on a graph. But I promise you, you can plug in any positive x value you want. The problem is, once you do like 3 to the 100th power, you're talking about a number that is hilariously massive. But you can do it. So this thing does have a range of 0 to infinity. And 0 is in parentheses because you can't ever have a y value of 0. But the y values can blow up and go off to positive infinity. What else? A few other things to note, some of the key points. Notice that 0, 1 is a point on the graph like I promised. If I plug in an x value of 0, it produces a y value of 1. If I plug in an x value of negative 1, then you're going to have a y value of 1/3, 1 over b. Unfortunately, it's kind of hard to see that, but here's negative 1, and then here's 0.5, and so the graph is a little under 0.5. This is going to turn out to be exactly 1/3. And, oh, it does show that. Very good. So negative 1, 1/3. And then a y value of positive, or excuse me, an x value of positive 1 here produces a y value of 3, and we have to get close to it, 1, 3. So it does indeed have all those characteristics that we looked at here just a second ago. The domain is good, x-axis is horizontal asymptote. We have characteristic 2 because the base is greater than 1, and all of these things were points on the graph. So very good, very good. Let's go back to the graphing calculator. So we tried 3 to the x. Let's see what happens when we try to do a negative exponent. Oh, negative 3 to the x. Now remember, we said we weren't allowed to do this. The base had to be a positive number. So we're playing pretend. We're playing what if C's here. And it disappeared. Where did you go? Well, it's because negative exponents lead to huge problems involving continuity. For the very simple reason that if you tried to take the square root of a negative number, if you try to do negative 3 to the 1/2 power, nothing's going to be there because that involves I. And graphs, when we look at graphs, those only allow you to have real x values and real y values. So you try to do a negative number in there and you're not producing anything. You can maybe produce this single point because 0, 1 will still work. There's also other points along the way that'll work, but it's not going to be continuous. You can't make a smooth graph out of it. So that's one of the reasons we have to restrict it. As soon as you go to a positive base, you're golden. You're back to that similar situation. 2 to the x. 1.2 to the x. You can do all kinds of things. That flattens it out, but it still has all the same properties of an exponential. What happens when you just do 1 to the x? Oh, you get something very boring. You actually just get the line y equals 1, which is a horizontal line that crosses through the y-axis at 1. And that makes sense because no matter what x value you pick, you plug it in, it's just going to spit out a 1 for y. So that's exactly the same as just the line y equals 1. It's the exact same thing. No change. So that's why, again, we say the base shouldn't be 1 because that's not interesting. That doesn't do anything for me. It doesn't look like an exponential curve kind of ought to look. So we're playing pretend here. Let's then look at the exponential function whenever we use a number between 0 and 1 as our base. So when 0.5 is our base, now all of a sudden it's a decreasing function. But again, that was promised to you. So in case 2 is not implying here, it's case 3, your function is always decreasing. The x-axis, though, is still a horizontal asymptote. The domain is still negative infinity to positive infinity. The range is still 0 to infinity. These three things are still technically true, although now 1 over b is 1 over 0.5, which is actually the number 2. So when I plug a negative 1 in for x, let's get closer to it. When I plug a negative 1 in for x, I get a 2 spat out for y. Still though, when I plug a 0 in for x, I get a 1 for y. When I plug a 1 in for x, let's just get it. I get the base itself, 0.5, as my y value. So it still works. It still does what we want. It's just now it's a decreasing function. So it looks a little bit different. That's okay. It's okay to be different. The closer you get to 1, so if you do like 0.9, 0.99, it starts to flatten out. It still has a little curve to it, but you have to go way out to start seeing it. So the closer you get to 1, it really starts to flatten out. Same if you go from the other side. So all kinds of interesting things are happening. Thank goodness for this Desmos graphing calculator. This thing rocks my socks because it keeps me from having to draw it, and it still looks pretty. We're actually not done with the Desmos calculator. Return. Now remember, we can still do transformations of functions. Remember how we added 3 to the entire function, so it shifted the graph up 3 units? We can multiply the entire function by -1, and it reflects the graph, something like that. We can still do all those transformations of functions that we learned about in chapter 2. We can still do it to the exponential function. It is not special. It is not exempt from that. It's just that some of those facts we said might get changed up a little bit because those facts only apply for the parent function. So here is the simple regular parent function, 2 to the x. Let's zoom way in. Give it that nice exponential curve again. Here's 2 to the x. If I add 1 to the entire function, So not to just the x, but to the whole function. Notice that it shifted the entire function up 1 unit. Now the horizontal asymptote is the line y equals 1, because even that gets shifted up a unit. So remember, those facts only apply to the parent function. You can also shift it down. You can shift it down, in this case, by subtracting 3 from the whole thing. You can go just to the x, and if I were to add 2 units, remember that's, you got to be very careful here. Come on, Desmos. I guess I'm going to have to put it in parentheses. If you add 2 units into the x here, it's going to shift it to the left. Now, it doesn't look like it did, but notice if I didn't add 2 units, and suddenly I add 2 units, it shifts it to the left 2 units. So suddenly things are just kind of working differently. I haven't done anything to manipulate the shape. I can add 2 units to the x, subtract 5 units from the y. I mean, you can get all kinds of wild with it. So all the standard transformations of functions we've already learned about apply. So I can translate it, I can shift it around left or right. I can also, and I'm playing with a little bit of fire here, I can also negate the entire function. And that will shift it about the x-axis. Then you say, whoa, pump the brakes, Josh. You said the base itself can't be negative. You're right, except that's not what's happening here. Technically, what's happening, the base is still positive 2. The base is not negative 2. So ignore the subtraction sign when you apply the exponent. The first thing you do is take 2 to the xth power, then you'd apply the negative sign. So the base is not negative 2, it's still positive 2, and then I'm just negating that entire function. That will flip it about the x-axis. Remember, if I tried to play some silly games and made the base negative 2, it ain't going to fly. Nothing's going to happen there. So the way it's written here, the negative 2 is being raised to the xth power. The way it's written here, x is still being, the 2 itself, positive 2 is being raised to the x. Then after I've already done the exponentiation, then I'm negating it. That's a huge key difference because that still produces a function in this case. So you can do all kinds of funny stuff. You can flip it about the x-axis. You can flip it about the y-axis. So there you go. The blue one is the original function. And it almost looks like, what's that? The 2 snakes, the medical thing where the snakes, what do they call that? It's early. I don't remember that off the top of my head. Anywho, you can do that to it. You can get all kinds of silly and rotate it and translate it. But just keep in mind that all of the natural kind of transformations of functions we've already discussed fully apply to exponential functions. They apply to all functions. So there's no reason that exponentials get a pass. Lastly, finally, we will talk about solving exponential functions, which is actually going to be exponential equations, which is actually going to be a little bit more of a nuanced thing at this stage than you might be ready for. We're not going to look at the general strategy for solving exponentials today. That actually involves logarithms, and we won't learn about logarithms till next time. But we can start with some basics and maybe see if we can use a little bit of reasoning. Let's try this one. Let's solve 3 to the 5x power equals 81. And notice whenever I say solve, what I mean is you need to solve for x. You need to figure out what x value can be substituted into your equation and make a true statement. Well, wait a minute, my x value is in the exponent itself. I can't just divide both sides by 3. This isn't 3 times 5x. That would be too easy. This is 3 raised to the 5x power. So we actually have not introduced a general strategy for solving this type of equation yet. So instead, at this stage of the game, we're going to need to use a little trickery. See if we can use a little bit of logic. The first hint I'll give you is that if this was 3 to the 5x equals 80, I actually would not be able to solve this using this tricky little method here. The reason is that there's something powerful, or there's something unique about 81, and this is a connection we're going to make here. 81 can be written as a power of 3. In fact, it's 3 to the 4th power. That's an important connection. So if it was just 80, 80 can't be written as 3 to a simple power. So that's not going to work in that case, but 81 is special. So in this section, or using these methods, we're going to have to rewrite so that both sides have the same base. That's going to be our little method of trickery. So now we're thinking that 81 can be written as 3 to some power, and yes, it can be written as 3 to the 4th. If, say, you didn't already know that, let's say you didn't know it was 3 to the 4th, just remember that we are not at the stage yet where we can solve these properly. So this trick is going to have to apply. Once you know that trick's going to have to apply, see if you can find a way to write 81 out. Let's see, let's try 3 squared. Well, no, that's going to be 9. Because our base is 3, let's see if we can get a common base here. 3 to the 3rd, well, that's going to be 3 times 3 times 3, which is 27. But suddenly 3 to the 4th is going to work. That's going to be 3 times 3 times 3 times 3, and it's going to end up being 81. So you suspect that solving this involves that little trick. So see if you can't re-express this as something that has that same base as the left-hand side. Now that you do that, look at this. The only way both sides will be equal here is if their powers are equal. Look, on the left-hand side, I'm taking 3 and I'm raising it to something. On the right-hand side, I'm taking 3 and raising it to something. The only way this will happen is if their powers are equal, is if 5x just equals 4. That's the only way. Because then whatever x I plug in here, it's going to give me the same thing here as it's going to give me here. In other words, set the powers equal to each other and solve for x. And that's just based off pure logical reasoning. You want 3 to the 5x to be equal to 3 to the 4th, then 5x needs to be equal to 4. And so now we can just quickly solve for x here. And you're going to get x equals 4/5. One thing I'll say, how can you be sure you found the correct answer? Check it. In other words, plug the x value you found back into the original function here. So we started with 3 to the 5x. We're going to plug this x value of 4/5 into that. 3 to the 5 times 4/5. And we're asking, is that equal to 81? Well, do a little simplification. You're doing 5 times 4/5. The 5s can cancel, and you're just left with 3 to the 4th. And you're asking, does 3 to the 4th equal 81? The answer to that question is yes. So this is a correct solution. X equals 4/5 is the only solution, or is the solution here. How do you know it's the only solution? That's actually a little more nuanced and not a question that we are going to answer today. Okay, so we don't have time to start another problem. We have less than 2 minutes. So I'm content that you guys can just chat or watch TikToks or something on your phone for the last minute or so of class.